So today, in the third part of Routh Hurwitz criterion, we will be discussing about stability of third order systems. This is one of the technique where we would be considering the internal multiplication of the coefficients and outer multiplication of the coefficients. So what is internal and external or outside coefficients of characteristic equation? Say this is your characteristic equation where these two terms are called as outside coefficients, and these two terms or coefficients are called as inside coefficients. So we have to simply have the multiplication of outside coefficients a3 into a0 and inside coefficients a2 into a1. What this philosophy or method states about that if internal multiplication internal multiplication is more than outside multiplication, then the system is stable. If internal multiplication of coefficient is or inside multiplication of coefficient is less than outside coefficients multiplication, then system is unstable. And this, if this multiplication is equal to each other, then the system is said to be marginally stable. So let us say this is your example, and we would be again verifying by using Routh Hurwitz criterion, that is Routh's table. So if we consider the inside coefficients multiplication, then it would be 8. 2 into 4 equal to 8. And multiplication of outside coefficients, it is 1 into 5 equal to 5. So inside multiplication is more than outside multiplication. Therefore, this system is a stable system. Now, this concept is to be verified by RH table. So, construct the RH table. These elements of this row, it is 1 and 4. Then this is second s raised to power 2 row 2 and 5 element. Others are derived from these two row elements. Here we are observing that there is no sign change in the first column of Routh array. Therefore, this system is stable. Now, this is another example considered where what you are observing that inside coefficient multiplication is 4, 2 into 4, 2 equal to 4, and outside coefficients multiplication is 4. So inside coefficient multiplication is equal to outside multiplication. Therefore, it should be, according to this method, it should be marginally stable. But as far as RH table is considered, it is constructed, and here you are observing that this row is ROZ, row of ROZ. As per previous discussions, we have concluded that if no sign change is occurring in the first column, but one ROZ exists, then the system is said to be marginally stable. So the method of internal multiplication and outer multiplication is verified by RH table as well. Now consider this example wherein sign change is there, 2 times sign change is there. It does mean two poles are lying in RHS of S plane and the system is unstable. For multiplication method, if we consider the inside multiplication, then it is 2, which is less than the outside multiplication, which is 6. System is unstable. But this multiplication method, coefficients multiplication method, is restricted to third order system only. So system should be third order system. If you are having system as third order system, then this method is applicable, otherwise not. Because in third order system you are having 4 coefficients. Inside coefficients are 2 and outside coefficients are 2. Symmetry is there, and this is one of the derived method actually. Next example, we are interested to have the conditional stability of third order system. You have to calculate the value of k for stability. This is your characteristic equation where a k constant is there. It should be the value of k constant for system to be stable. So construct Routh's array. You would get the elements like this. According to Routh-Hurwitz criteria, all elements of first column of Routh array should be positive. So one condition, that is k should be equal to should be greater than 0. Another condition, this factor should be greater than 0. So 16 minus k greater than 0 does mean k should be less than 16. So for systems to be stable, k should be greater than 0 and k should be less than 16. It does mean 0 is less than k is less than 16. This is the range where the system is stable. If you are interested to have the system as unstable, then k should be less than 0 and this factor should be less than 0, or this should be less than 0. It does mean k would be greater than 16. So range would be k is less than 0 and k is greater than 16. System is unstable. For marginal stable, this row element should be 0. One row should be ROZ. So for making this row as 0, this coefficient as 0, then k should be equal to 16. It would be 0, 0 element. So this row would be ROZ, row of zeros, where the system would be marginally stable. So k equal to 16, where system is marginally stable. Now consider the multiplication method. For system to be stable, internal multiplication should be greater than inside multiplication should be greater than outside multiplication of the coefficients. So this 16 should be greater than k, or k should be less than 16. For system to be unstable, this inside multiplication 8 into 2, 16 should be less than k. So k should be greater than 16. Now for marginally stable, inside multiplication should be equal to outside multiplication, that is 16 equal to k. Therefore this is 16 equal to k. Now in this example, we are again asking about the value of k for system to be stable, unstable or marginally stable. This is the system where you have to apply Routh's array, and constructing Routh's array for stability condition, this all elements of this column should be positive. So for making this as positive, it should be greater than 0 and k should also be greater than 0. System to be stable, k should be greater than 0 and this factor, that is 40 into 48 minus 12k divided by 40, must be greater than 0. On solution, k is less than 160. So range would be k is greater than 0 and k is less than 160, that is 0 is less than k is less than 160. Now for system to be unstable, k should be less than 0 and this factor should also be less than 0. So here you would be getting k is greater than 160 and k is less than 0. For system to be marginally stable, this factor should be equal to 0, therefore k is equal to 160, the gain of the system where the system is marginally stable. If the system is marginally stable, it means the system would be having poles on imaginary axis, and marginally stable does mean the system is sinusoidal, cosinusoidal, or that is the oscillatory system. If oscillatory system is there, it means there would be some oscillations, and then if the system is oscillatory, oscillations are there, the frequency of oscillations would be there, then how we would be able to determine the frequency of oscillations? So for that you have to construct the auxiliary equation. Since you have put this element, first column element of s raised to power 1 row as 0, then the characteristic equation, auxiliary equation is 40s square plus k. So 40s square plus k equal to 0. This is the auxiliary equation where k is equal to 160. So s square is equal to minus k over 40 equal to minus 160 over 40 equal to minus 4. On solution, j omega equal to plus minus j2. So frequency of oscillation omega equal to 2 radian per second. Now in this example we have again asked about the value of k for stability. And this is the system where k is the gain, k is greater than or equal to 0. Initially, for applying Routh-Hurwitz criteria, the first condition is to have the characteristic equation of the system. And the characteristic equation of the system is given by 1 plus gs into hs equal to 0. Here gs would be equal to k into this factor, and hs is s minus 2. So 1 plus k into s minus 2 divided by s plus 2 whole square into s minus 2, this factor, equal to 0. On solution you would be getting s square into 1 plus k plus 4s into 1 minus k plus 4 into 1 plus k equal to 0. So if you would be constructing the Routh's array, your elements would be these one of the first column of Routh array. System to be stable does mean 1 plus k should be greater than 0. 4 into 1 minus k should be greater than equal to 0, greater than 0. 4 into 1 plus k should be greater than 0. So all coefficients of all elements of first column of Routh array should be greater than 0 for system to be stable, but being to considering the positive sign of the elements. So if 1 plus k is greater than 0, does mean k is greater than minus 1. If this factor is there, then k is less than 1. So your two conditions are there, that is k is greater than minus 1 and k is less than 1. So if you would be asked about the range, then you can specify that minus 1 is less than k is less than 1. But it is not right, because the condition of gain is given as k is greater than or equal to 0. Therefore, your condition for system to be stable would be 0 is less than or equal to k is less than 1. Now, if you are having exponential term in numerator of transfer function, in that case, what should be the value of k for system to be stable? See, this is that open loop transfer function GS, where we have considered k into e to power minus st divided by s into s plus 1, and the feedback loop gain HS is unity. Now, initially you have to take the linear approximation of e to power minus st, which is 1 minus st. Then proceed accordingly. GS is equal to k into 1 minus st over s into s plus 1, and HS equal to 1. Now, first condition to evaluate the value of characteristic equation for applying Routh's Hurwitz criterion. Therefore, the characteristic equation is given by 1 plus GSHS equal to 0, where it would be s square plus s into 1 minus kt plus k equal to 0 on solution of these two equations and on application of these two equations. If this is your characteristic equation, then construct the Routh's array. S square elements would be 1k, and this is 1 minus kt, and calculated value is k. System to be stable does mean the all elements of first column of Routh array should be positive. So obviously 1 minus kt is greater than 0 and k is greater than 0. So 1 minus kt is greater than 0 does mean k is less than 1 over t and k is greater than 0. So range will be defined as 0 is less than k is less than 1 by t. Now, in this example again we have considered the system of e to power minus s. On linear approximation of e to power minus s, it is 1 minus s. And on solving, the characteristic equation would be s to power q plus 5s square plus s into 9 minus k plus k equal to 0. Applying Routh's reconstructing rule, then your coefficients would be like this. Elements of first column of Routh array would be these one. System to be stable, it should be greater than 0 and k should also be greater than 0. From here you can calculate that k is less than 45 over 6, that is 15 over 2. So 0 is the range would be 0 is less than k is less than 15 by 2 or 7.5. So in this way we have considered the all methods of the Routh's array. Here we have discussed about the Routh's criterion. First column element at 0, one row as row of z, zeros, that is called as ROZ. If one ROZ is occurring in a system, then the system is oscillatory. If two ROZ are there, repeated roots are there, and the system is unstable, even if you are getting first column elements at 0. If three ROZ are there, we have considered the example. If you are having all elements, if you are having any one of the coefficient as negative in the characteristic equation, then the system is unstable. So in this way we have considered a lot of the conditions where the stability of the system using characteristic equation and application of Routh's table can be considered, can be evaluated. but there are some restrictions of the or the limitations of Routh-Hurwitz criterion is there. This criterion is applicable only for linear systems. Therefore, if you are having e to the power minus st or any exponential term, you have to linearize that one. It doesn't provide the exact location of poles on the RHS or LHS of S-plane. In case of characteristic equation, it is valid only for real coefficients, not for imaginary coefficient of the characteristic equation. So these are some limitations of Routh-Hurwitz criterion, and in this way we have completed all aspects or covered all aspects of Routh-Hurwitz criterion. Thank you.